The Pacific Ocean east of Japan looked calm again after the shaking stopped. Fishing boats returned to harbors. Tsunami advisories faded from television screens. Bullet trains resumed their schedules. Yet beneath that seemingly quiet stretch of ocean floor, something immense may still be unfolding. What happens when a magnitude 6.7 earthquake strikes directly inside one of the most dangerous subduction systems on Earth? Can one rupture quietly rearrange stress deep underground without people realizing it? And when scientists begin talking about twin quakes, are they describing coincidence or the early stages of a much larger tectonic chain reaction? On May 15, 2026, a magnitude 6.7 earthquake struck about 30 miles or 49 kilometers east-southeast of the city of Ofunato along Japan's northeastern Pacific margin at a depth of roughly 27 miles or 43.6 kilometers. The earthquake occurred within the broader Japan Trench subduction system, one of the most mechanically stressed plate boundaries on Earth. It was not large enough to produce catastrophic destruction on the scale of the 2011 Tohoku megathrust disaster, yet the event immediately attracted scientific attention because of where it happened, how it happened, and what had already happened nearby during the previous months. The concern is not simple fear-mongering. Japan's offshore tectonic system has a long history of clustered ruptures, segmented megathrust failures, and stress-linked earthquakes that sometimes arrive in pairs or sequences. The phrase twin quake may sound dramatic in headlines, but the underlying geology is very real. Along certain subduction margins, one earthquake can redistribute crustal stress into neighboring locked zones, increasing the probability that another large rupture could follow. Sometimes that second rupture arrives within minutes, sometimes within days, sometimes years later. And sometimes it never comes at all. Understanding why requires looking far beneath the ocean floor into the violent mechanical engine driving Japan itself. Japan exists because of subduction. The islands sit at the collision zone of several tectonic plates, but the northeastern portion of the country is dominated by the Pacific Plate, descending beneath the Okhotsk microplate along the Japan Trench. The Pacific Plate moves westward at roughly 3 inches or 8 centimeters per year. That speed may seem slow compared to human movement, but at geological scales, it is extremely rapid. Over decades and centuries, enormous strain accumulates because the descending slab does not slide smoothly downward. Instead, large portions of the plate boundary become locked by friction. This locking process is central to understanding megathrust earthquakes. As the Pacific Plate continues pushing beneath Japan, the overriding crust bends and compresses. Rocks near the trench deform elastically, almost like a giant spring being loaded with energy. The ocean floor itself may slowly warp downward, while inland portions of northeastern Japan may subtly shift toward the Pacific. GPS measurements have repeatedly shown this gradual crustal distortion occurring over enormous regions before major earthquakes. Eventually, friction can no longer hold the plates together. When the locked zone suddenly ruptures, centuries of accumulated strain may release in minutes. The overriding plate snaps seaward and upward. Massive sections of the fault can slip by dozens of feet or several meters. That abrupt displacement generates seismic waves and sometimes tsunamis if the seafloor moves vertically. The 2011 magnitude 9.1 Tohoku earthquake demonstrated this process with horrifying clarity. In some regions near the trench, the fault slipped by more than 160 feet or 50 meters. Entire sections of northeastern Japan shifted permanently eastward. The rupture propagated across hundreds of miles of fault surface. The tsunami that followed devastated coastal communities and triggered the nuclear disaster at the Fukushima Daiichi nuclear power plant. But subduction systems rarely behave in simple ways. Not every rupture releases all stored stress. Some earthquakes only partially unload the fault while transferring strain into neighboring segments. This is where the concept of earthquake interaction becomes critically important. When a large earthquake occurs, it changes the stress field around it. Geophysicists often analyze this using Coulomb stress transfer models. The idea is relatively straightforward, even though the mathematics are highly complex. A rupture relieves stress in some regions while increasing stress in others. Imagine snapping one section of a tightly stretched fabric. The tension redistributes unevenly across adjacent areas. Some neighboring zones become temporarily more stable, while others move closer to failure. This mechanism is one reason scientists monitor whether a large offshore Japanese earthquake may be followed by another significant event nearby. The northeastern Japan Trench is not a single smooth fault. It is segmented into regions with different frictional properties, structural geometries, sediment thicknesses, hydration states, and thermal conditions. Some portions rupture frequently in moderate earthquakes. Others remain locked for centuries. Stress transferred from one rupture can potentially destabilize adjacent segments that were already critically loaded. This possibility explains why recent seismic activity has drawn scientific scrutiny. In December of 2025, a magnitude 7.5 to 7.6 earthquake struck offshore near Aomori and Hokkaido. Then, on April 20th of 2026, another large offshore earthquake between magnitude 7.4 and 7.7 occurred within the same broad tectonic system along the Japan Trench. Although Japanese authorities did not formally classify the pair as a true earthquake doublet, seismologists noted that both ruptures occurred within related subduction structures. Now, the May 2026 magnitude 6.7 earthquake near Ofinato adds another layer to the evolving seismic picture. The key issue is not simply the size of the quake itself. A magnitude 6.7 earthquake releases substantial energy, but it remains far smaller than the energy associated with megathrust earthquakes above magnitude 8. The deeper concern involves what the rupture may indicate about the current stress evolution of the northeastern Japan subduction interface. Earthquake sequences often reveal hidden fault behavior. Sometimes a moderate earthquake is merely an isolated stress release. Other times it acts as a foreshock. A foreshock is not defined by its physical characteristics at the moment it occurs. It is only identified afterward if a larger earthquake follows. This creates one of the greatest difficulties in earthquake science. A magnitude 6.7 earthquake offshore Japan may statistically most likely remain the largest event in its sequence. Yet a small percentage of such earthquakes have historically preceded much larger ruptures. This uncertainty creates enormous tension in hazard forecasting. After the April 2026 offshore event, the Japan Meteorological Agency issued advisories acknowledging a slightly elevated probability of another major earthquake occurring within roughly 1 week. Importantly, the estimated risk remained low, approximately around 1%. To the public, 1% may sound insignificant. But from a seismological perspective, a 1% probability over such a short time frame represents a meaningful increase above normal background seismicity. That distinction matters. Earthquake prediction, in the precise sense, remains impossible. Scientists cannot determine exact times, locations, or magnitudes of future ruptures. However, probabilistic forecasting is different. Researchers can identify periods when tectonic systems appear more stressed or dynamically unstable based on seismic interactions and statistical behavior. The reason Japan receives such attention is because subduction zones sometimes produce cascading rupture behavior. The historical examples are striking. The 1944 Tonankai earthquake and the 1946 Nankai earthquake ruptured adjacent portions of the Nankai Trough only about 2 years apart. Together, they represented sequential failures of neighboring megathrust segments along southwestern Japan. Geological evidence suggests similar paired or clustered megathrust behavior has happened repeatedly through Japanese history. These events reveal an important property of segmented subduction systems. Large plate boundaries are rarely uniform. Instead, they contain partially independent rupture zones, separated by structural barriers, bends, sediment accumulations, or variations in rock properties. Sometimes one segment ruptures while another remains locked. Yet the first rupture may increase loading on neighboring sections until they eventually fail as well. This segmentation concept is central to modern earthquake science. The Japan Trench itself likely contains multiple frictional domains with different rupture behaviors. Some areas may creep slowly without major earthquakes. Others remain locked and accumulate stress over centuries. The boundaries between these domains are especially important because they can either halt ruptures or allow them to cascade into larger failures. The 2011 Tohoku earthquake surprised scientists partly because the rupture propagated farther toward the trench than many earlier models predicted. Before that event, some researchers believed shallow portions near the trench might slip more gently through aseismic creep. Instead, the earthquake demonstrated that extremely large shallow rupture was possible, producing enormous vertical seafloor displacement and catastrophic tsunami generation. That realization transformed understanding of northeastern Japan's seismic potential. Today, scientists closely examine whether moderate offshore earthquakes may illuminate changing conditions within the subduction interface. One major factor involves fluid pressure deep underground. As the Pacific Plate descends beneath Japan, it carries water trapped within oceanic sediments and hydrated minerals. Increasing pressure and temperature at depth cause dehydration reactions that release fluids into surrounding rock formations. These fluids can migrate upward along fractures and fault zones. Elevated pore fluid pressure reduces effective frictional resistance on faults, making rupture easier. This means some earthquakes may occur not simply because tectonic stress rises, but because friction weakens locally due to fluid movement. Fluid-rich fault zones can behave unpredictably. They may experience slow slip events, earthquake swarms, or transient stress changes that alter rupture probabilities. Modern seismology increasingly recognizes the importance of fluid migration within subduction environments. Another crucial factor is viscoelastic stress transfer. After a major earthquake, Earth's crust and upper mantle continue deforming for years or even decades. Rocks deep beneath the brittle crust behave more like extremely slow-moving putty than rigid solids. Following a large rupture, these ductile layers gradually flow and redistribute stress throughout the tectonic system. The 2011 Tohoku earthquake likely continues influencing stress conditions across northeastern Japan even now. GPS networks across Japan have documented long-term crustal adjustments since that disaster. Some regions continue rebounding, while others remain compressed. Offshore stress fields are still evolving. This means present-day earthquakes may partly reflect tectonic consequences of ruptures that occurred many years earlier. The May 2026 earthquake near Ofinato therefore cannot be viewed in isolation. It exists within an active tectonic landscape already altered by previous major events. Seismologists also examine earthquake focal mechanisms to understand rupture geometry. Offshore Japanese earthquakes may occur on the plate boundary interface itself, within the descending Pacific slab, or inside the overriding crust. Each type reflects different mechanical processes. Megathrust interface earthquakes occur where the two plates directly contact each other. These are the events capable of generating giant tsunamis and catastrophic coastal deformation. Intraslab earthquakes occur deeper within the descending Pacific Plate as it bends, fractures, and deforms under immense pressure. The sinking slab experiences both compression and extension depending on depth and geometry. Some deep earthquakes originate from mineral phase transformations or dehydration embrittlement within the slab itself. Upper plate earthquakes occur within crustal faults above the subduction zone and may reflect crustal stress adjustments linked to deeper tectonic forcing. The reported depth of about 27 miles or 43.6 kilometers places the May earthquake within a tectonically complex zone where distinguishing the exact rupture environment becomes especially important. If the earthquake occurred on or near the megathrust interface, scientists would pay close attention to possible stress interactions with neighboring locked segments. If it occurred within the slab, the implications for future megathrust activity might differ substantially. Even moderate earthquakes can reveal hidden fault coupling conditions. One of the most difficult challenges in subduction science is determining which sections of a plate boundary are locked and how strongly they are coupled. Researchers use GPS deformation, repeating microearthquakes, seismic tomography, marine geodesy, and laboratory rock friction experiments to estimate coupling behavior. Yet direct observation remains impossible because the critical fault surfaces lie miles beneath the ocean floor. Every significant earthquake provides new data about how stress is distributed underground. Some ruptures stop abruptly against barriers, suggesting stronger locked regions nearby. Others propagate smoothly through multiple segments, indicating broader mechanical connectivity. Aftershock patterns also reveal fault geometry and stress redistribution. After large offshore earthquakes, scientists frequently observe complex aftershock migration patterns. These migrations may indicate fluid movement, slow slip propagation, or stress diffusion through fractured rock volumes. Sometimes earthquake clusters migrate along the trench over days or weeks, suggesting dynamic interaction between neighboring fault patches. This raises an unsettling question for Japan's current seismic sequence. Could the recent earthquakes represent independent ruptures within a naturally active system, or are they part of a larger evolving stress cascade? The answer remains uncertain because earthquake systems are inherently nonlinear. Small changes in stress can sometimes trigger enormous ruptures if nearby segments are already critically loaded. Conversely, even very large earthquakes may fail to trigger adjacent faults if structural barriers remain intact. This sensitivity makes earthquake forecasting extraordinarily difficult. Dynamic triggering adds another layer of complexity. When an earthquake occurs, seismic waves radiate outward through Earth's crust. These passing waves can temporarily alter stress conditions on distant faults. In some cases, large earthquakes have triggered seismicity hundreds or even thousands of miles away. Most triggered events remain small, but occasionally larger ruptures occur. Static stress transfer, by contrast, involves permanent stress redistribution after fault displacement. Both dynamic and static effects may influence subsequent earthquake probabilities. Scientists studying Japanese subduction systems also investigate slow slip events, which represent a strange middle ground between locked faults and ordinary earthquakes. During slow slip episodes, portions of a fault gradually slide over days, weeks, or months without generating strong shaking. These events release energy too slowly to produce damaging seismic waves. Yet they still redistribute stress throughout the fault network. Some slow slip events appear to precede major earthquakes. Others occur harmlessly. Understanding their role remains one of the biggest open questions in modern tectonics. Japan possesses one of the world's most advanced seismic monitoring networks precisely because of these uncertainties. Dense arrays of seismometers, ocean bottom instruments, pressure gauges, and GPS stations continuously monitor crustal deformation and offshore seismicity. This instrumentation has revealed that subduction zones are far more dynamic than once believed. Rather than remaining locked silently for centuries before sudden rupture, plate boundaries may experience constant micro-adjustments involving tremor, slow slip, fluid migration, fracture propagation, and transient stress pulses. Large earthquakes emerge from this restless background state. In statistical terms, most earthquakes follow predictable aftershock decay patterns described by Omori's law, where aftershock frequency decreases over time. However, when two similarly sized, large earthquakes occur in related fault zones, scientists examine whether the second rupture may have been independently triggered by stress transfer from the first. Historical Japanese earthquakes provide important case studies. The 19th century and 20th century records contain multiple examples of segmented megathrust behavior along Japanese trenches and troughs. Geological evidence from tsunami deposits also indicates prehistoric earthquake clustering. Sediment cores extracted from coastal marshes and offshore basins preserve traces of ancient tsunamis. Layers of marine sand washed inland by giant waves reveal that some megathrust events occurred in sequences separated by relatively short intervals. These records extend earthquake history far beyond written documents. The Japanese archipelago's vulnerability arises from its location within the Pacific Ring of Fire, a massive horseshoe-shaped belt of subduction zones surrounding the Pacific Ocean. Here, oceanic plates descend beneath continental or island arc systems, generating intense volcanism, earthquakes, and crustal deformation. Subduction zones produce Earth's largest earthquakes because of their enormous fault areas. A shallow crustal fault may rupture across tens of miles or several dozen kilometers. A megathrust interface, by contrast, can rupture across hundreds of miles and involve slip surfaces thousands of square miles in area. The resulting energy release becomes almost unimaginable. Magnitude scales are logarithmic, not linear. A magnitude 7 earthquake does not represent merely a slightly stronger event than a magnitude 6. Each full magnitude step corresponds to roughly 32 times more energy release. A magnitude 8 earthquake releases about 1,000 times more energy than a magnitude 6. A magnitude 9 releases roughly 32,000 times more. The real story unfolds across immense spans of time and space. Stress may accumulate for centuries before release. Fault segments may interact across hundreds of miles or several hundred kilometers. One rupture may subtly influence another years later. Some earthquakes relieve danger locally while increasing it elsewhere, and sometimes the most dangerous processes remain invisible. Locked portions of the subduction interface produce no immediate warning signs. They may sit silently accumulating strain while surrounding regions experience swarms of smaller earthquakes. In some cases, quiet zones known as seismic gaps become especially concerning because they may indicate strongly coupled fault patches storing large amounts of elastic energy. Researchers continue debating whether portions of the Japan Trench currently exhibit such conditions. Advanced marine geodesy has become increasingly important because many critical deformation signals occur offshore beyond ordinary land-based GPS coverage. By placing instruments directly on the seafloor, scientists can measure subtle tectonic movement above submerged fault zones. These observations are gradually improving understanding of how stress evolves between major earthquakes. Yet despite extraordinary technological advances, the fundamental unpredictability of rupture nucleation remains. Scientists still do not fully understand why one critically stressed fault suddenly fails while another remains locked. Rock friction experiments reveal highly unstable behavior near failure thresholds. Tiny variations in fluid pressure, mineral composition, fault roughness, or stress orientation may drastically influence rupture initiation. Earthquake systems behave less like simple mechanical machines and more like chaotic networks operating near critical states. This is why every offshore Japanese earthquake attracts global scientific attention. The concern is not merely about one event. It is about what that event may reveal regarding the current state of one of Earth's most powerful tectonic systems. For now, the magnitude 6.7 earthquake east-southeast of Ofinato stands as a significant but not catastrophic reminder of the forces beneath Japan. Whether it ultimately becomes part of a larger sequence, a foreshock, or simply another isolated rupture may only become clear with time. The Pacific Plate continues descending, the trench continues locking, stress continues accumulating, and somewhere beneath the cold waters offshore Japan, the next rupture is already being prepared by geology itself.